Hello and welcome to this session on RDBMS and SQL. Today we'll focus on functional dependencies. Just to refresh your memories, we have looked at ER models. So we discussed if you were a database designer, how would you get started with this whole business of creating a schema? So we talked about entity sets, relationship sets. We talked about how to derive, how to see these entity sets, and how to reduce this diagram to a table structure. So we looked at different properties of entity sets, different kinds of relations, and so on. We also looked at two different notations. So this kind of notation and the UML-like notation as well. I showed you lucidchart.com, where you could create these diagrams online. With that, we are ready to discuss functional dependencies. So why do we need functional dependencies? So here is a table for you. Do you see any problem with this table, with this relation? Um, when I ask this question, students very quickly figure out that there is a lot of redundancy in this table. For instance, if it is given that Einstein always works for the physics department, and the physics department always works from the Watson building, then I don't have to repeat this information for every physics department. So I know physics department is in Watson building already, but I have repeated it here. So this kind of redundant information causes several anomalies, as we say. Um, Anomalies cause issues at the times of insert, delete, and update. So here, whenever I insert another row with physics, I should be careful that I insert Watson as the building. So there are certain table designs which are considered good, and certain table designs which are considered not so good. So the objective for us ahead is, can we come up with a way to design or to arrive at better database designs? So with that, let's get started with functional dependency. So we say one attribute uniquely identifies another attribute, and we use this notation to refer to the same. For example, here ID uniquely identifies name. So we write it as ID, right arrow, and name. So when I say ID uniquely determines name, given an ID, there is only one value for name, which I can look up from this table. That's what I mean. So what are the other functional dependencies that you can see in this table? Well, ID uniquely determines almost every other column in this table, including itself. So ID uniquely determines ID uniquely determines department name, salary, name, and so on. Alright, so here is a question for you. From the following instance of relational schema R, can we conclude that A functionally determines B and B functionally determines C, A functionally determines B and B does not functionally determine C, and so on? Take a minute, pause this video, and work this out for yourself. If you are done, unpause this video now, and here is the right answer. B does not functionally determine C is all we can say from this instance. So one thing that you should understand from this example is that we cannot determine functional dependencies given a specific instance. Functional dependencies are associated with the real world, the domain, and not the specific instance. FDs impose constraints on what a relation can carry and what a relation should not carry. So just because for example, a value of 1 in A seems to have a value of 1 in B, and value of 2 in A seems to determine a value of B as 3, we cannot say that A functionally determines B. So we don't know. It's just a matter of another row addition which might violate this ability to determine. But a change in value, one counter example is sufficient to say that something does not functionally determine. So given an instance, the only thing we can say about functional dependency is what kind of functional dependencies do not hold. So if you look at this, B does not functionally determine C because B in the first tuple has a value of, has a C value of 1, but B in the first tuple has a C value of 0. Okay, so in the instructor table, we saw that ID uniquely determines all the attributes of the table, including itself. In such cases, we call those attributes as keys. So ID is a key and it uniquely identifies all other attributes in that relation. Okay, so let's do a quick revision. We are talking about interrelated data. We modeled data as a relation, which is a subset of a Cartesian product. And we saw that this makes a lot of sense to uh, design tables this way. So this became the foundation to arrive at the idea of tables, and we further go ahead and build a database management system on top of the knowledge we have on relations. So we saw that even querying can happen this way. So a query language takes multiple relations as input and gives out one relation as output. As a procedural language example, we looked at relational algebra. Here is an example for relational algebra, and the modern day SQL reflects the basic ideas of relational algebra. So this is what we have seen now, and today we looked at what keys are and what a functional dependency is. So a few more terminologies for you. Um, uh, Prime attribute. All attributes that form the key are called prime attributes. So here is an example. Let's say R1 is a relation with A, B, C, and D as the variables, the attributes. AB, so I use this notation where I underline the attributes which are prime attributes. So if AB is the key, then A and B are called prime attributes. So here is a question for you. Consider the relational schema R with E, F, G, H, I, J, K, L, M, N, and the set of functional dependencies. E, F determines G, F determines I, J, E, H determines K, L, K determines M, and L determines N on R. What is the key for R? So by definition, the key for R contains all those prime attributes, all those attributes which together would functionally determine every other attribute of R. So let's take each of these choices and work it out. So E and F. So if I know EF, I can determine G, right? So from EF, trivially, I can determine E and F themselves. So these are trivial dependencies. We don't write it, but it's implied. So EF determines EF and G. With EF and G, what more can I determine? Looks like nothing more. So EF alone is not sufficient. So let's look at EFH. With EFH, EF determines G, F determines IJ. So EFGH, EFGIJ. So let me see if I can write this. Okay. So now we are looking at the second choice, which is EFH. So what all would EFH determine? Okay, so EFH would determine trivially EF and H, and from the first dependency here, we identify that EF determines G. So I know this can determine G as well, and F determines IJ. So let's write down IJ, and E and H. Do I know E and H? Yes, I already have determined E and H. So since I know E and H, I can determine K and L, and from K I can determine M, and from L I can determine N. So I can determine M N as well, right? So if you look at it, from EFH, I can determine all the attributes of R. So EFH is a key for R. E alone will not determine all attributes. We have already seen it, because E and F together do not determine all the attributes. But what about the option C? E, F, H, K, and L. Well, so this should determine all attributes, but then we have some additional attributes beyond what we need to find to determine um, all the attributes. So since we have additional attributes, we call this as a super key and not just a key. So for this question, the best choice is B. Um, some relations may have many candidate keys. You may choose any one of them to be the primary key. Okay. So here is a question for you. Um, Relation R has 8 attributes: A, B, C, D, E, F, G, H, and the functional dependencies are given to you. How many candidate keys does the relation R have? Okay, so first we figure out, we take individual attributes and try to find out how many other attributes that it can identify. We call this as the closure of that attribute. So for example, uh, A closure. So what is A closure? A closure would mean from A, I what all can I determine? So from A, I can determine BC. So the A closure written as A plus would of course have A, and along with A now it will also have BC. That's because of this functional dependency given over here. From B, I can figure out CFH. So C is already here, and so let's add FH. And if I know CFH, I can from F I can identify EG. And now that I know A, B, C, F, H, E, G, so I know C and H, so I can figure out G. So G is already there. From B, I can find C, F, H, so that's also there. So pretty much I have everything except D, right? And there's no way to figure out D from the given functional dependencies, because D doesn't exist on the right side of the functional dependency, right? So A plus or A closure is A, B, C, E, F, G, H without D, all right? And similarly, if you compute B closure, E closure, and F closure, you will see that we can compute everything except D. So that means if I add D to my set, so A and D together will identify all the attributes, so it forms a key. So AD forms a key, BD forms a key, ED forms a key, and FD also forms a key. So we call these as candidate keys. Since we have multiple keys, we have candidate keys, and we can choose any one of these and make the primary key. You will see in future that knowing a primary key is useful, because when we do the table design, we mark certain columns as primary keys, and then we use them to link or join to tables. So what's a super key? A super key, as we already discussed, is the combination of a candidate key with additional attributes. So here is a question for you. Which of the following is not a super key in a relational schema with attributes VWX, YZ, and primary key VY? So the primary key is given to you as VY. Uh, so so we a super key should have vy and some additional attributes. So wherever you see vy with some additional attributes, that's a super key. So which of these is not a super key? Well, the option B is not the super key because we miss the prime attribute y there. One other concept that is quite important is avoiding redundant dependencies. So consider a relation R with attributes A, B, and C with functional dependencies F given as follows. A determines BC, B determines C, A determines B, and AB determines C. Do you find any redundancy in these FDs? Well, yes, FDs can also be redundant. So, for example, in this case, if I tell you that B determines C, right? So if I tell you this functional dependency B determines C, then any attribute along with B will also determine C, right? So we already see some kind of redundancy in the functional dependencies. So the challenge ahead of us here now is that if you and I were to um, identify functional dependencies in a domain, given a set of attributes and relations, can we come to some kind of a standard form? So we call this as the canonical cover. And to compute a canonical cover of a set of FDs, we apply a few rules in a repeated fashion. The first rule is called absorption. So we say that if I have two functional dependencies like these, A determines BC and A determines B, then I could simply drop this second one, A determines B. Why? Because this A determines B, C simply means that A determines B and A determines C. So that's what it implies. So you don't have to have another explicit functional dependency A determines B. We can also drop extraneous attributes as in this case, like what we discussed in the previous slide. So if AB determines C and B determines C, so B already determines C. So in that case, adding any attribute to the left would also determine C. That is quite obvious. So we don't need uh, those extraneous attributes in the functional dependency. So B determines C is sufficient. You could, so now you have two functional dependencies, A to BC and B to C. So if you take these two functional dependencies and look for either absorption or dropping extraneous attributes, you will see that you can do some further refinement here. So we are dropping an extraneous attribute. So we know that A determines BC and B determines C. So basically, I can say that A determines B and A determines C is what is implied from the first functional dependency. Since A determines B and A determines C is no more required. The second one, the A determines C is no more required because if A determines B and B determines C, then A determines C is kind of obvious. So we drop this to get to A determines B and B determines C. So the canonical cover that we have reached at is A determines B and B determines C. Okay, so let's move on to discuss some normal forms. So let me refresh your memories again. All attributes that form the key are called prime attributes. So I use this notation of underlining the attributes that are prime attributes. So in this case, A and B are prime attributes. Just to just to check your understanding, let's try this quiz. Please pause the video after reading the question and work it out yourself before proceeding with this lecture. let a relation R with three columns A, B, and C be a relation where the candidate keys are A, B, and AC. We choose AB as the primary key. So what are the prime attributes? So if your answer was A and B, then you are wrong. Uh, Prime attributes are the attributes that make the keys, okay, not necessarily the primary key. And in this case, we have A, B, and AC, which are both candidate keys. So A, B, and C are prime attributes. So please be careful with the definition of prime attribute. We have already seen that this relation is a bad relation, and I told you that this kind of design causes anomalies. So there are three kinds of anomalies. Delete anomaly: when deleting a value of an attribute, we should not lose the value of some other attribute. So let's say there is only one professor in a specific building. So if I were to delete that professor, I also lose the information about how many buildings exist, for instance. So that's an example of delete anomaly. We also have insert anomalies. To insert a value of an attribute, we need to know the value of other attributes which we might not know at the time of insertion. Storing the same data at multiple relations may lead to consistency issues as well. So when you are inserting, uh, let's say, another professor at the physics department, you should be careful that you put him in the Watson building with the appropriate budget. Um, and we have to remember this every time when we insert a specific professor. So we don't like this. This is an insert anomaly. Similarly, we could also have update anomalies at the time of updating a specific professor. So how to avoid these anomalies, we look at better ways of designing these tables. In this slide, I introduce you the normal forms. As we go higher up the chain, so we say that it, it schema which is in the second normal form is better than the first normal form, and it avoids certain kinds of anomalies. And similarly, a third normal form design is better than a second normal form design, and so on. So here is an example of first normal form. A relation is in first normal form if and only if the domain of each attribute contains only atomic values. Now look at this example. So in this case, Pooja Singh has two phone numbers, and having two values in one attribute is something which we don't like, and this makes our life difficult when we do relational algebra queries. So to convert this to a first normal form, I have many choices. So here are two choices. In the first choice, I simply have one value in the telephone number column, and I in order to insert another phone number for Pooja Singh, I simply add one more row and add the second phone number here. Now now this table is in first normal form, but the problem is there is too much redundancy of data just to add one phone number. So here is another way to take this table to this first normal form. I can have telephone number 1, telephone number 2, and so on. Where the number of columns matches the maximum number of phone numbers I have for anybody. So in this case, there's only one row for Pooja Singh with both her phone numbers here. Okay, is this a good design? Turns out that this is also not a good design, because I need to upfront know how many telephone numbers any person may have, and if this changes and if someone takes additional phone number, then I have to add a column. Adding a column needs an update to all the other tuples in that relation, which we do not like to do. Um, so these are so this is an issue. So we prefer to have a single column structure rather than a multiple column structure like this. Let's move on to second normal form. A relation is in second normal form if and only if it is in the first normal form and there is a partial dependency, or there is no partial dependency, sorry. So what is a partial dependency? So let's take this example. I have a manufacturer, let's say Forte, and Forte manufactures X prime, some model. um, so the full name of the model is Forte X prime. This need not be a concatenation of the manufacturer and model, but in this case it happens to be. And we also have a manufacturer country, which is Italy. Okay, so we have a bunch of toothbrush models here, the manufacturers and the country information. Do you see any problem with this table design? Well, you need to know the functional dependencies before you could answer this question. So the functional dependencies are given to you. Let's say, again, I repeat, we don't infer functional dependencies from the instance of the table given, but these functional dependencies are given to you, let's say, by the domain experts. So here it says manufacturer alone determines manufacturer country. So this means that Forte is always in Italy. So given the manufacturer, I can tell you the country, which means Forte is always in Italy, right? So if Forte is always in Italy, uh, then it makes no sense to repeat it for every model that we have. So this is what we call as a partial dependency. A non-prime attribute, uh, non-prime attribute uh, is not should not be functionally dependent on any proper subset of the candidate key. So here the candidate key subset contains uh, sorry about, yeah, so the candidate key contains a manufacturer and model, but the manufacturer country determines only on the subset of the candidate key, which is bad. So it should depend on all the prime attributes. So since it depends on subset, we have a problem, and now we want to change the design. So how would you change this design so that this partial dependency is removed? Well, it's simple. We take the manufacturer country out of the table and add it to the. We simply remove it and we add it to the to another table. So we have a manufacturer country table. Here there is no partial dependency, and similarly here too now we don't have any partial dependency. So we say that this schema is in second normal form. So here is a question for you. Sorry. Is the relation R with ABC, where A and B are prime attributes, in second normal form? Well, I should say AB is a key, specifically a primary key in this case. Assume AB and AC are candidate keys. Um, um, so is R in second normal form? Note that B determines C is a functional dependency given to you. Okay, so since B determines C is a functional dependency given to you, R is in second normal form. Why? Because we don't have any non-prime attribute in this relation. Since AB and AC are candidate keys, every attribute A, B, and C are prime attributes. So there is no non-prime attributes. So there is no question of partial dependency here. Okay, we'll stop here for the day. In the next session, we'll continue with the third normal form and beyond. Thank you.